recording, so I'll share my screen. Okay, I think everything is fine. Everything fine, right? The guy who is watching, is he fine? Yeah. Okay. So we can talk about some interesting things. So now we are doing time series analysis, right? You started on Tuesday with Nigahoda. Time series analysis. Actually, I love time series analysis. It is my best thing. It's the best part of econometrics for me. I love it so much. It's not like I don't love panel data, but I feel like I am more comfortable with time series. So like with this course, whenever I'm assisting this course, I love it after the midterm. You know, before the midterm, at times it can get boring with these ordinary least squares, things you already know, one are the same things. It's a little bit boring for me. Maybe not for you, I don't know. But with time series is something which I really like, so we can talk about it. By the way, you know what time series data is, right? What's time series data?
It's an annual data for one country.
Yeah, it must not be annual. It can be monthly, it can be high frequency, whatever. But it is data for one subject over a period of time. Times you have a time span, time series data. Okay. Actually, today we are going to do unit root tests. That's the only thing we'll do today. Then next week we'll do something else. But I will give you an overview as I always do. Then we can talk about unit root tests. So for the remainder of this, why are you smiling?
Because I appreciate what you're doing.
Is that why you're smiling?
Yeah.
Okay. Is that why you're also smiling?
What? Sorry? I missed.
Why are you smiling?
I don't know.
You don't know why you're smiling?
It just happened. Yes. I keep smiling and I always have happiness. Yes. Yeah.
Okay.
Like the cap as well.
Oh, my cap?
Yeah.
This cap is a nice cap, you know. Really? Okay. So for the remainder of this semester, for the for the remainder of this semester, this is what we are going to do. For time series analysis, of course, we will start with unit root tests. Unit root, I will explain everything, don't bother. The first thing we'll do, and this is all we'll do today. Then next week, we'll do co-integration. How do I spell it? Johansson co-integration test. We'll do vector error correction model. Vector error correction model. And you also do you also do Granger causality tests next week. Then most probably the week after, which will be the last week, I'm sure. Then we can do auto regressive distributed lag AROZL. So I think this is what we'll do for the rest of the semester. So today we'll do unit root tests. Next week we'll do these three because they are like you can do all at once. Johansson co-integration test, vector error correction model, Granger causality test. And then the week after, we'll do AROZL, and I think that will be it. So these are time series models. Okay, so today we'll start with unit root tests. Sorry? One more class? Two more classes, I think. You have a class with Nigahoja on Tuesday. Next week, and then we'll do practicals on Friday. The following week, Tuesday, and then Friday.
But the Friday and the last week is no classes. For you, for your class, you're going to take it in Nigeria.
No.
Because the end of the class is 8, not 9.
Yes, but really? We will not have time? Okay, maybe I can record. Yeah, I understand. Classes end on the 8th, Thursday, right? So we will not have chance on Friday. Okay, if we don't have chance, I can record and send a video. Or, since Nigauja has 3 hours on Tuesday, maybe she might do 2 hours and then I do 1 hour. I don't know. I'll talk to her. Whatever. So today we are doing unit good tests. What are unit good tests? Why do we do unit good tests? Why? Any idea? Sorry? Yes. We are trying to check if the series is stationary or not. What is stationarity? What is a stationary series?
It should have constant mean, variance, and covariance. So all should be in a constant y over time without any effect or impact from the previous.
Exactly. So a stationary series is a series which has, how am I supposed to write everything? Constant mean, constant variance, and constant auto covariances for every given lag, right? So it means at lag 1, lag 2, lag 3, at all lags, the mean is constant, the variance is constant, and all the auto covariances are constant. If these conditions are satisfied, then we can say it's a stationary series. Okay, so with time series analysis, before doing anything, the first step is always to run unit root tests. Why? Why is it necessary? Okay, of course, you said we are running unit root tests because we are trying to check if it is stationary. But why? Why should we check if it is stationary? Why should we not just go ahead? We have our data. We should just go ahead and use whichever method, either ordinary least squares or co-integration. Why must we check if it is stationary first before we know what to do?
Because it determines the methodology or the way that we're going to do our data.
Mm-hmm. Yes.
The use of the average non-stationary will lead to
Spurious regression. Yes, that's one of the reasons. There are at least 3 reasons. Yeah, you're just shaking your head. You're not saying anything. Spurious regression. Okay, I'll tell you. So actually, it's important for us to check if our series, our data is stationary. Why? Because depending on if it is stationary or not, we have to treat it differently. For instance, if it is stationary, we will treat it differently from if it is not stationary. You cannot treat all of them the same. And there are reasons for this. The first reason is that if it is stationary or not stationary, that is the stationarity or otherwise, will affect the behavior of the variable, right? So, should I write it? I'll just write here behavior as properties. So whether it is stationary or it is non-stationary, it will affect the behavior and the properties of the series. What do I mean by this? For instance, a series which is stationary, if you have a stationary series, it means that if there is any shock to the system, right, this shock will die away gradually. But if the series is non-stationary, then if there is any shock to the system, this shock will remain forever. It will not die away. It's either it will remain the same or it will increase, but it will not go away. It will remain persistent forever if the series is non-stationary. But if the series is stationary, then if there is any shock to the system, the effect today will be more than the effect next year, which will be more than the effect the following year. So as you keep going in time, the effect keeps reducing. It keeps dying away gradually. So it's important. That's the first point. And the second point is what she said, spurious regression. What's a spurious regression? And Nigahoja likes asking this question. And I can guess she will ask this question in the final exam. What is spurious regression? She always likes asking it. What's a spurious? Is it spurious or spurious? Anyhow you can pronounce it. What's a spurious regression? Any idea? What is spurious regression? I don't know if it's spurious or spurious. Anyhow you pronounce it.
It's a regression that seems perfect, but we have a higher theory.
Yes. Yes, that's correct. It's a regression which seems as if it is good, but in reality it is bad. What do I mean by that? You know, if you run a regression, if your R squared is high, you want it, right? High R squared means high explanatory power. If your T statistics, T ratios are significant, it means your coefficients are significant. It's good. So a good regression has high R squared, significant T ratios.
So it's a,
but
the variable is so sensitive to the changes.
Okay, I'll explain. But a bad regression has a low explanatory power, low R squared, and insignificant T ratios, right? Now, if you take two unrelated things, for instance, if you run a regression of financial development, you regress it against economic growth. Of course, you expect to have a high R squared because these two macroeconomic variables are related. You know, financial development is related to economic growth, right? So you expect to have a high explanatory power. But if you run a regression between two things which are unrelated, for instance, GDP and somebody's age, what's the relationship between your age and GDP? There's no relationship. So if you run a regression, let's say dependent variable is GDP, independent variable is somebody's age, because they are not related, then you expect that the R squared should be low and the T ratio should be insignificant, right? That's what you expect because these variables are not related. But then you only have this case if the variables are stationary. If these two variables are stationary, then if they are unrelated, then know that you have a low R squared. But if they are related, then you have a high R squared. But there is a problem now if the variables are non-stationary. If these variables are non-stationary, then even if they are unrelated, you might still have a high R squared. And so the high R squared now will make it look as if it is a good regression, whereas it is a bad regression because there is no relationship between age and GDP. So you expect to have low R squared, insignificant T ratio. But because one of them is non-stationary, one or both, it is not as if both of them must be non-stationary. If just one is non-stationary, it's enough. So if at least one of them is non-stationary, then you might have this spurious regression. You understand? So that's why it is important for us to check if it is stationary or not, because if it is not stationary, then we cannot use ordinary least squares, for instance. If it is stationary, okay, of course we can use ordinary least squares. So the method you will use will depend on if it is stationary or not. So we have to check. So what's the third reason? The third reason why it's important for us to check if it is stationary or not. Sorry? Yeah, no, ADF is one of the tests. We'll talk about it soon. Okay, I'll tell you invalid hypothesis testing. Now, guys, if you have stationary series, if all your series are stationary, then you can do your hypothesis test, and your hypothesis test will be valid. But if at least one of them is non-stationary, then any hypothesis testing you're doing is invalid. I can assure you. Why? Because the T ratios you have will not follow a T distribution, and your F statistic will not follow an F distribution. You know, one of the assumptions we are using for hypothesis testing is that these things are normally distributed, and the T statistics are following T distributions, while the F statistic is following F distribution, right? But if you have non-stationarity, then any hypothesis testing you're doing is invalid, it's misleading, because your T ratios will not follow T distribution, and your F statistic will not follow F distribution. So I think these 3 reasons are enough, and I'm sure Nika Hoja will ask in the exam. She likes asking it. Maybe she might ask you to define spurious regression, maybe. And maybe she might ask you that what are the reasons why you think it's important to test for non-stationarity? Why is it important to check if series are stationary or not? So if you can give her these 3 reasons, I think it will be good, right? Okay, now we have 2 types of non-stationarity. Types of non-stationarity. What are they? 2 types. Who can tell me? Nobody? You are checking your notes? 2 types of non-stationarity. Ikra. You don't know? You why? Anybody? Okay, I'll tell you. We have random walk.
Oh yeah.
Random walk with drifts, and we have trend stationary process, right? These are 2 types of non-stationarity. You know, at times people always get confused that why are they calling it trend stationary when it is a type of non-stationarity. Of course, it is trend stationary process, but it is non-stationarity. It simply means that it is stationary around a linear trend, but it is non-stationary. So these are the 2 types of non-stationarities. Random walk with drift, we can also call it stochastic non-stationarity. Why trend stationary process, we can also call it deterministic. How are they spelling? Non-stationarity. Sorry? Yes, you have to say something.
Like the stochastic means like there is errors in it. And
yeah, whenever the stochastic simply, yes, of course, if there is an error term, it means it's stochastic. Okay, I will show you something, don't bother. So these are the 2 types of non-stationarities we have. Okay, I can draw if you want. I don't know how to draw on it. For random walk?
Yeah.
Okay, I'll tell you what random walk is. But you did not do random walk in FINA 603, FINA 503 investments.
No.
Random walk, you cannot predict.
I do have it also in the portfolio, but I mean, I didn't understand the stochastic itself.
Something like this. How do we call this one? This. In fact, by the way, these 3 graphs, which of them is stationary and why?
First one.
The first one? What about the second one?
It has a trend.
Okay. This one is stationary because, of course, you see it has a constant mean. So, actually, this is a white noise process, right? It's stationary. This one is stationary around a linear trend. It is non-stationary because look at, if you take this to be the mean, you see the mean keeps changing. So the mean is not constant. So this is trend stationary process. Trend stationary process. It is stationary around a linear trend. Then this is random walk. Random walk simply means you cannot predict. You don't know if it's going like this or like this or like it is random. It happens in financial markets.
That's why the error exists, right?
Of course, it's random, yes. You know, in financial markets, with efficient market, they assume that stock prices follow a random path. You cannot predict the next movement of the stock price. Okay. So actually, this is random walk. Random walk process. So this one is stationary, white noise. These 2 are non-stationary. These are the 2 types of non-stationarity. Now, if something is non-stationary, it means we are trying to make it stationary, right? So this first one, how can we make it stationary? This trend stationarity. How can we make it stationary?
By taking the trend.
If you remove this trend, if you take away this trend, you have this, right? So this trend stationary process, we can make it stationary simply by detrending. So if you detrend a trend stationary process, it becomes stationary. Just detrend simply means take away the trend. That's how we can induce stationarity here. Then with random walk process, how can we induce stationarity? How can we make it stationary? By
adding the
differencing,
which is the uncertainty. So that's why it's the error term that's not been added. That's why it's been called.
Yeah, I understand. Don't talk. Forget about error term. You're trying to make it complicated. But just put it in your mind that for trend stationary process, we can induce stationarity. We can make it stationary by detrending. Just take away the trend. It becomes stationary. And for a random walk process, we can make it stationary by differencing. Actually taking the first difference or maybe second difference, depending on, you understand? Okay. So these are the two types of stationarity. And I showed you the graphs. Everything fine? So trend stationary process can be made stationary by detrending, while random walk with drift can make stationary by differencing, right? So maybe Negauja might ask you in the exam, how can you induce stationarity in this kind of process, whatever. Okay, now the next thing I'll talk about is, we'll get into the practicals very soon. I just want to give you an idea. The next thing I'll talk about is order of integration. You heard of it before? Order of integration. Have you heard of it before?
Yeah, the I1, I0, at which level that we put the differences.
Okay. Where is the duster? Before I tell you about it, let me just tell you something briefly. So guys, in this course, we will focus on this type of stationarity, random walk with drift. We will not focus on trend stationarity. But know that trend stationarity is also a type of non-stationarity. So for random walk with drift, let me show you the equation, right? This is how the equation is. I'm sure you have seen it. Something like that. You saw it before?
Yeah.
So actually you're regressing a variable against the same variable that lack value. Because this variable and this variable are the same, right? But this is lack value. Forget about the details anyway. This is a constant, of course. This is the intercept, right? Which is drift. We're here of drift. It can be random walk with drift. Drift simply means intercept. So if you put this intercept, it means drift. If you remove the intercept, it means there's no drift. Now, our problem is this coefficient, this phi, right? If this coefficient is equal, it can be equal to 1, it can be less than 1, or it can be greater than 1. Less than 1, equals to 1. If this coefficient here is less than 1, then it means it is stationary. Stationary. Then if this coefficient is equal to 1 or bigger than 1, it means it is non-stationary. So both of them means it is non-stationary.
You told us that the equivalent one doesn't exist.
I understand, I'll tell you. Both of them means it is non-stationary. So for it to be stationary, it must be less than 1. If it is equal to 1 or bigger than 1, it is non-stationary. Now, this case where it is equal to 1 is unit root process. If it is equal to 1, then we say it is unit root, right? If it is bigger than 1, it is explosive. Explosive. I don't want to explain more than that because it can get complicated, but just put that in your mind. So these two cases are non-stationarity, but if it is equal to 1, it is unit process, which is still non-stationarity. If it is bigger than 1, it is explosive process, which is still non-stationarity. Right? Okay. Now, in this course, we are not going to focus on this explosive process. So our only focus is unit root process. Right? So we are considering in this course that non-stationarity means it is equal to 1, which means it has a unit root. We don't focus on the explosive process, but I'm just telling you that you should know that it must not only be equal to 1, it can also be greater than 1. If it is greater than 1, it's explosive. If it's equal to 1, it is unit root. Okay. Now, I hope we have time. Okay. Now, I'll tell you something about order of integration. Let me write it here. So when we are checking unit root, when we are testing unit root, guys, if something has unit root, it means it is non-stationary. If it does not have unit root, it means it is stationary, right? Put that in mind. So with order of integration, you can define it in various ways. You can simply, for instance, let me say I0. What's I0? It is integrated of order 0, right? We have I1. I1 means, I'll explain number that. Integrated of order 1. I2 means integrated of order 2. Okay. Guys, remember I told you that for this course, we are focusing only on random walk with drift. We are not talking about train stationarity. And if you have a random walk with drift, which means it is non-stationary, if you want to induce stationarity, you do it by differencing, right? So you have a non-stationary series. How many times are you supposed to difference this series in order for it to become stationary? If you difference it once and it becomes stationary, then we'll say it is I1. It is integrated of order 1. But if you are supposed to difference it twice, maybe you difference it the first time, but it is still non-stationary. You need to difference it the second time before it will become stationary. Then in that case, we'll say it is I2. You understand? But if it does not need differencing, if it is stationary, then it is I0. So I0 simply means stationary at level form. The data is in its raw level form, it is stationary. You don't have to difference it. I1 means at level form, it is non-stationary. You need to difference it once for it to become stationary, which means it is stationary at first difference, right? So I1 means non-stationary at level form, but stationary at first difference. So you need to difference it just once. At the level form, it is non-stationary. You difference it once, it becomes stationary. So that is integrated of order 1, I1. Now with I2, it means at level form, it is non-stationary. You difference it once, that is first difference. It is still non-stationary. You difference it twice before it becomes stationary. So in this case, it is stationary at second difference, which means it is I2. Yes, I'll tell you. So I2 integrated of order 2 means non-stationary at level, also non-stationary at first difference. Once you difference it the second time, it becomes stationary at second difference. Correct? Understood? I0 means stationary at level. I1 means non-stationary at level, but when you difference it once, it becomes stationary at first difference. I2 means non-stationary at level, You difference it once, at first difference, it is still non-stationary, and then you difference it twice, it becomes stationary at second difference. I guess you understand that. In other words, we can still say, another way we can put it is that if something is I0, it means it has no unit root. If a series is I1, it means it has one unit root, single unit root, one unit root. And if it's I2, it means it has two unit roots. So you can define it anyhow you want. Why not the same thing? Are you okay? Okay. So it's important for us to perform unit root tests, because unit root tests will tell us if the variables are I1 or I0 or I2, right? And depending on the results we have, we are going to know the method to use. For instance, let me just tell you this, then we can do the practicals. For instance, let's say you're carrying out a study. You have, let's say, 5 variables or 4. You have your dependent variable and you have some independent variables. You need to check unit root for each variable there. Each variable. Now, if you check your unit root for all the variables, you can have 3 types of results. Either all variables are I0, all are I1, or we have mixed order of integration, which means some are I1, and some are I0. So, guys, when you run your unit root test, these are the kind of results you have. It's either all your variables are I0, or all of them are I1, or maybe you have a mixed order of integration. Maybe some of them are I1 and some of them are I2. Depending on this case, you will know what to do. For instance, if all your variables are I0, if your unit root test tells you that all your variables are I0, then the method you're supposed to use will be ordinary least squares, which of course you know. So you directly use your basic regression, ordinary least squares, and you can do your study. But if all of your variables are I1, then you have to do co-integration. This is the method you use. And if you have a mixed order of integration, which means some of them are I1, while some are I0, then you have to do ARODL, autoregressive distributed lag. So you discover that it's important to carry out unit root tests, because depending on the results you get, you will know what method to use. You cannot just say, I'm using co-integration, I'm using ARODL. Why? You need to do your unit root test first, right? Okay. So we'll do the unit root test now. One other thing I will let you know about is that you see I1, this is the most common case that you will find. Like if you do too many studies, you will find that most of the variables are I1. It's very rare to see a case where all of your variables are I0. Of course, there are cases where, let me correct something. Most of the variables you will find will be I1. Some of them will be I0, some of them, but most of your variables will be I1, these macroeconomic variables. And I2 is very rare. It's very rare to find variables which have 2 unit roots. For I3, I4, I5, forget it, it does not exist. There's no variable which has 3 unit roots. Yes? I will tell you, yes. So you will not find any variable which is I3. There's no variable which has 3 unit roots. Very few variables have 2 unit roots. So you might find some I2 variables. It's rare. But most of the variables in economics and finance are I1. They have a single unit root. Some might be I0. Yes, so that's why we don't even talk about I2. That's why if you're doing a study and you do unit root tests for your variable and you discover that your variable is I2, change the variable. Either you delete the variable totally or you use a different proxy, because there is no method you can use. You see all these methods here are talking only about I1, I0. So if you have any variable which is I2, just change it. Find a different proxy. Don't use it. Okay. I think that is understood. So now, how can we test for unit roots? That's our main issue now. So we have understood what unit root is. The whole idea with the unit root test is that we are trying to get the order of integration. We are trying to check if it is stationary. Is it stationary at level, or is it stationary at first difference, or is it stationary at second difference? We are trying to get the order of integration, because order of integration will tell us the method to use. So the big question now is that how can we test for this unit root in order to get this order of integration? Anybody knows? What kind of test can we use to test for unit root?
Unit root from ADF.
Yeah, the test, the name of the test, you don't know? The conventional test? You mentioned one before.
The ADF 1979.
Okay, I'll tell you. Guys, to test for unit root, we have so many tests. That's the first thing I'll tell you. But for this course, we are going to focus only on the conventional tests. So we'll see just 3 tests. Now, I'll tell you a good story. Many years ago, many studies that they were doing in the 1950s, 1930s, they were using ordinary least squares basic regression to do all these studies, right? Whether it is time series, whether it is cross-sectional, they were using ordinary least squares to do all these studies. Later on, they figured out that most of those studies were wrong. Why? Because they discovered that some of these time series are not stationary. And if your series is not stationary, if it has a unit root, you cannot treat it the same as if it is stationary. If it is stationary or non-stationary, you have to treat it differently. So they began looking for methods on how to test for unit roots. So the very first guys who carried out a study to do this were some interesting guys, Dickey and Fuller. They did a study in 1979. So they came out with a Dickey-Fuller test, right? Or you can call it DF test. So this was one of the initial tests they came out with to test for unit root. But then this DF test has a problem. You know, what's the biggest problem in time series? Time series, the biggest problem.
Autocorrelation.
Autocorrelation, yes. So the biggest problem in time series is autocorrelation. So this DF test, even though it was used to test for unit root, but it did not solve the autocorrelation problem. So they had to augment this test by adding lag values of dependent variable in order to solve the autocorrelation problem. So they augmented this DF test into what is now known as augmented. That is ADF test. So it is the same test, but they just augmented it. They tried to improve the test. So after that, some other 2 guys, Phillips and Perron, came out with their own tests in 1988 to test for unit root. So you can call it Phillips-Perron test, PP test, right? Then, so these two tests are unit root tests. I'll tell you something. Then in 1992, some other guys felt like, can we come out with a test which reverses the hypothesis of this test so we can confirm our analysis? So they came out with KPSS test. KPSS test, 1992. So actually, guys, ADF tests and PP tests are unit root tests, but KPSS test is a stationarity test. They are different. What do I mean by they are different? Let me write it down here. Unit root tests, ADF and PP. This unit root test, the null hypothesis is that there is unit root. The alternative hypothesis is that there is no unit root, right? But for the KPSS test, stationarity test, it's not easy writing this thing, so the null hypothesis, it reverses the hypothesis. So here the null hypothesis will instead be that there is no unit root, or you can say it is stationary. As you know, when they say it is there is unit root, what does it mean? It means it is non-stationary, right? All right.
Yeah.
Unit root means it is non-stationary. If they say there is no unit root, it means it is stationary. That's the meaning. Okay. Look at something. So there are three tests we are going to focus on. Now, I'll do the practicals in a second. We are focusing on ADF tests, PP tests, and KPSS tests. You know, KPSS is the names of some 4 guys, Kwiatkowski, Phillips, Schmidt-Shin, very long name. They just abbreviated KPSS. Now, these ADF and PP tests are unit root tests. You know, in this case, they name the test after the null hypothesis. You don't have to cram it. Just know that the test is named after the null hypothesis. Yeah, the null hypothesis is telling you that there is unit root, which means it is unit root test. With KPSS, the null hypothesis is telling you that it is stationary, which means it is stationarity test. So you have to be careful. ADF and PP are unit root tests, while KPSS is stationarity test. At the end of the day, they are testing the same thing, but be careful. So when the ADF and PP tests came about in 1979 and 1988, these were the hypotheses. Null is telling us that there is unit root or it is non-stationary, or alternative is telling us that there is no unit root or it is stationary. But then these 4 guys, KPSS, they said, let's try to do a confirmatory analysis by reversing the hypothesis of the ADF and PP test. So this null hypothesis should instead be the alternative here, and this alternative should be the null. So if you perform these 2 tests, it's some kind of a confirmatory analysis. That's why most of the times, as Miguel will always say, if you use your ADF and PP test and you have conflicting results, maybe some of them are telling you that there's unit root, some of them are telling you that there's no unit root, then you can use the KPSS test to confirm your results. It's like a confirmatory test, right? Okay, you understand that. Now, before the practicals, one last thing I'll tell you. I keep saying one last thing, but I keep saying so many things. These tests have like the unit root tests, each of them, ADF and PP, have 3 models each, 3. Like for instance, you have the general model, it's trend and intercept. You have the intercept model. And you have the non-model. Non-model simply means neither trend nor intercept. So the ADF test has 3 different models. The PP test has 3 different models. The KPSS test has just 2 models. The KPSS test has just 2 models. The non-model does not exist for the KPSS test. Okay, let me tell you what these models mean. You should not get confused. Guys, if you see this equation, this is intercept, right? Drift. So if you're trying to run the test and you include this intercept and there's also a trend, it means in your model there's both intercept and trend, which is the general model. You can still perform the test without the intercept. Sorry, without the trend. This is intercept. You can perform the test without the trend and just with the intercept. Intercept only model. And you can perform the test with neither trend nor intercept, which means you don't include intercept, you don't include trend. So they call it non-model. Something like that. Okay. So directly we'll do the practicals now. Any questions? Fine? Okay. Let me look for data. Which data would I use now? The practicals is very easy. Where is FINA 614? So we have 20 minutes. We'll do the practicals for 20 minutes. I think it should be enough.
Yeah.
Okay, I have this data. So I have 1, 2, 3, 4 variables. So I'll put them now on eViews. You know how to put this thing on eViews, right? From 1990 till when? 2019. 1990 to 2019. So data, what are my variables? Carbon dioxide, financial development, GDP, CO2, financial development, GDP, and I think population. So now I'll just copy my data and paste on eViews as I always do. As usual, you paste the first cell, right? Okay, we have our data. We are going to use log form, but I'll tell you something about log form. You know, I always keep telling you that it's always good to use log form because it solves a lot of problems, especially problems like heteroscedasticity, normality, and whatever. But know that log form does not solve stationarity problem. So don't think that if your series is non-stationary and you take log form, it will solve it. Never. The only way to solve stationarity is if it is random walk, you take differencing. If it is trend stationary process, you take detrending. So don't ever think that log form will solve stationarity, no chance. But even though it does not solve stationarity, we still always use log form because it solves other problems. It rescales the data, reduces the variability, you know all of that. So I will take log form. Generate lane CO2, which is equals to log CO2. So I will just put here financial development. Let me do it fast. GDP. Population. Okay. So we have our variables in this study, 4 variables, right? We have lean CO2, lean FD, lean GDP, and lean population. We have to check for each of them whether it is stationary or non-stationary. And guys, we are checking both at level and it's a whole process. For each test, you have to check 3 models, both at level and at first difference for each variable. You understand the task? So let's start with ADF test. ADF test, we'll check it at level and we'll check it at first difference. So the first variable is lean CO2, right? So what you do is that you open the variable, come here to view, come to unit root test. Yes, you can do it, but let me see. Come to view, unit root test. Okay, so if you come here, you see the test. You have augmented decay Fuller, Phillips Perron, and KPSS, right? These are the 3 we are using. Forget about the others. So let's start with augmented decay Fuller. You choose the test. You have to check it both at level and phase difference, right? And you have to check for each of these three models. So I will start with level. And even though we have three models, please always start with the general model. That is the least restrictive model, which is trend and intercept. After trend and intercept, go to trend, go to intercept, and then none should be the last, because none is the most restrictive model. So level, trend and intercept. Don't change anything here, use automatic selections, because if you try to change it, you just use automatic selections. Then click OK, you have your results. Now, once you have your results, for some of them, they will give you probability value and they will give you the test statistic. For some of them, they will not give you probability value, they will give you only test statistic. Either way, you should know what to do. So, of course, you know we can use 1%, 5%, 10%, right? But let's use 5%. We always use 5%, right? So if you're using probability value, you know what to do. If your probability value is higher than 5%, you cannot reject. If it is less than 5%, you can reject. Now, what are the hypotheses? For unit root tests, you see the hypothesis, right? Okay. Looking at these results, here, probability value is bigger than 5, so we cannot reject, right? If you cannot reject, what does it mean? It means it is non-stationary at level, because we are doing level. We will finish with level before we go to first difference. So based on ADF tests using the general model, it is non-stationary at level. You can also make this decision using T statistic. You know, you compare your test statistic to critical values. One thing I'll tell you about this ADF and PP tests is that these are one-tailed tests. One-tailed tests. One-tailed tests. What do I mean by one-tailed tests? One-tailed test means that, what have I done? Sorry. One-tailed test means that in order for you to reject the null hypothesis, this test statistic must be negative. It cannot be positive. This value here, it should not be positive. If it is positive, there is no way you can reject the null hypothesis. It must be negative. If it is negative, it should be more negative than your critical value. If it is more negative than your critical value, then you can reject the null. But if it is less negative, then you cannot reject. If it is positive, you cannot reject. So you see here, it is negative. Of course, it is good, but it is not more negative than critical value, because you see here is -2, but here is -3. So it is less negative, which means you cannot reject. If here was maybe like -5, more negative, then you can reject. So in order for you to reject the null hypothesis, if you're using the T statistic, the test statistic, first of all, it should be negative. And secondly, it should be more negative than critical value. Then you can reject. If it is positive, you cannot reject. If it is negative but less negative than critical value, you cannot reject. Understood, right? So at times it is confusing. That's why people always like using probability value to make the decision. The probability value is easy, but not all of the tests will give you probability value. Some of them will give you just test statistic and critical value. So you need to know how to use it. So in this case, you see it is less negative, so we cannot reject. And what is the null hypothesis? The null is telling us that there is unit root, right? So if you cannot reject, it means there is unit root. But that is just for one model. Now we need to use the other model. So again, once you have the results, come to view, come to unit root, come here, just change this model from trend and intercept to intercept, which is the second model, and then click OK. My EVS is messing up. I don't know. You have the results, right? Again, you see probability value is bigger than 5, so you cannot reject. Also, if you use this one, it is negative, good, but it is not more negative, so you cannot reject. So those two models are telling us that there is unit root. Okay, now come to unit root test, come to the last model, which is the most restrictive model, non-model. Again, you cannot reject. You see, it's even positive, no chance, you cannot reject. So you discover that using ADF tests for this carbon dioxide variable, right, all three models are telling us that there is unit root. So that is it for ADF tests. Now, that is for level. Come again to unit root. Let's check it now for first difference. So just change from level to first difference, and then start back again with trend and intercept, and then check it. You see that you can reject, right? Which means,
It's stationary at level 1.
oh my God.
First difference level.
So if you reject this and you accept this, it means it is stationary. So it means at level it was non-stationary, but at first difference it now becomes stationary, which means it is I1. It is integrated of other one because it is non-stationary at level, but when you difference it once, when you take the first difference, it becomes stationary. So it is I1 according to that, but that's just one model. We need to do the other models. So again, view, unit root, check for intercept, and okay. Again, you see you can reject. It is more negative than critical value. So it is confirming that it is stationary at first difference. Next, unit root, non-model. Here you go with the majority, I'll tell you. Non-model, again, you see, you reject. It is more negative than critical value. So based on this test, just for ADF, this is just ADF, augmented decay Fuller. We have checked all three models, and all three models are telling us that it is non-stationary at level. When we go to first difference, all three models are telling us that it is stationary. So according to ADF test, it is I1. But we need to check PP test as well, Phillips Perron. So come to view, unit root, just change from ADF to Phillips Perron, and then repeat the process again. Come back to the level, trend and intercept, and then check one after the other. When you're done with level, you come to first difference, and then you check all three models, and then you see. So in some cases, each of the models for both tests will tell you that the results are the same. First, it is I1, it is non-stationary at level, stationary at first difference. But most probably you will find some conflicting results. Maybe, as she asked, maybe for these three models, maybe two of them are telling you that it is stationary, one is telling you that it is non-stationary. You can, first of all, if you have these conflicting results, then you should do KPSS, right? So, for instance, let's check this one, level, trend and intercept. So you see here, you cannot reject, right? You cannot reject, it's higher than 5%, and it is less negative than critical value. So at level form, it is non-stationary. Now, if I come here, I go to the next, intercept. Again, you cannot reject. So it is non-stationary at level. Again, non-model. You cannot reject. So you see for all three models, both ADF and PP tests are telling you that they are non-stationary at level. Let's see first difference. Come to view, unit root, just change to first difference and then come back, repeat the process. If you see first difference, you reject, which means it is stationary. This one is more negative than critical value. Again, unit root, change the model to intercept, and you see you reject. So it's interesting, right? Non-model, again, you reject, right? So you discover that both ADF and PP tests are telling us that this particular variable is non-stationary at level, but stationary at first difference, which means I1. But there are some variables that you do it and you discover that it is stationary at level, which means I0. In some cases, it is non-stationary at first difference, non-stationary at level, non-stationary at first difference, but becomes stationary at second difference. That's I2. right? Okay. So once you do it, let's check KPSS. You know, KPSS is the confirmatory test. So just change this guy to KPSS, Kwiatkowski, Phillips, Shin. You see, they have just two models. The non-model is not effective for them. Again, go to level, and then start with the general model, train and intercept. And then now, guys, remember I told you that ADF and PP are one-tailed tests, right? Which means it must be negative. With the KPSS test, it is not one-tailed test. So which means this guy must not be negative. It can be negative or positive. And by the way, here they will not give you probability value KPSS. So you have to use the test statistic to make the decision. How do you make the decision? In order for you to reject the null, this test statistic must be bigger than the critical value, bigger in absolute value, as you know, right? If this test statistic is bigger in absolute value, it must not be negative, whether negative or positive, but it should be bigger in absolute value. If that happens, you can reject the null. And remember, for the KPSS test, the null and alternative are the reverse of ADF and PP. Like here, the null is that it is stationary, while alternative is that it is non-stationary. So if the test statistic is bigger than critical value, then you can reject the null and accept the alternative. But if it is less than critical value, then you cannot reject the null, which means it is stationary, right? So you discover that first, you start by performing ADF and PP tests, and if you have results which confirm each other, then no need to do KPSS. But if you have conflicting results, maybe some of the models are telling you that it is stationary, some are telling you that it is non-stationary, then you can perform the KPSS test as a confirmatory test to confirm your results. Whatever the KPSS test tells you, you go with it, right? Okay, that is it. So guys, what I'll tell you is that, you see, we have done it just for one variable, carbon dioxide. But in your study, you can have like 4 variables. So you will take each variable and you will perform this test for each variable, both at level and phase difference, which means you take the first variable, carbon dioxide, you go to ADF test, you go to level, you check all 3 models. After you go to phase difference, you check all 3 models. You now go to PP test, you go to level, you check all 3 models, you go to phase difference, you check all 3 models. You go to KPSS, you go to level, you check all 2 models, you go to phase difference, you check all 2 models, and then you're done with that variable. You move to the second variable and you repeat the process. Then you have to summarize your results in a table. I think Nigahoja did show you how you can put your results in the table. Okay, let me show you. There is an article Nigahoja wrote with Hoja and Mohamed Kakir.
Yeah, that table, yeah.
I will show you now. I can find the article. Niga. Yes, this is the article. Guys, we have 3 more minutes, but
I have a question.
Maybe 225 instead of 220. I can finish 225, right?
Just to confirm. So for the T statistics for the KPSS or whatever that test is, to be able to reject the null hypothesis, the T statistics should be bigger than the critical.
Yes, for KPSS tests, it must not be negative. The test statistic must not be negative. In order for you to reject the null, it should be bigger than critical value in absolute value. Okay. It should be bigger in absolute value. But with ADF and PP tests, first it must be negative, and it should be more negative. If it is positive, you cannot reject. If it is less negative, you cannot reject. So it should be negative and more negative before you can reject. Understood? Okay, guys. So, like I said, 225, I'll be done. Let me just show you something. So you see, this is unit. You see how they tabulated their results? So after you do here, they had 1, 2, 3, 4, 5 variables. So you see, you take the first variable, you take ADF, you check 3 models. You see, this is the first model, which is a general model with trend and intercept. This is the second model, which is the intercept only model, and this is the third model, which is a none. After you do PP, you check all three models. They did not do KPSS here, but you can add KPSS if you want, 2 models. And then you do it for level. After you do same for first difference, right? And then you can indicate with stars. You know, 1 star can mean, no, 1 star can mean it is, you can put 1 star to mean it is significant at 10%. If it is significant at 2%, sorry, if it is significant at 10%, you can put 1 star. If it is significant at 5%, you can put 2 stars. If it is significant at 1%, you can put 3 stars, right? If it is non-significant, don't put star. So you can design some beautiful tables like this, and at the end you decide. Like, look at this variable, carbon dioxide. You see here, there are no stars. There are no stars here for carbon dioxide, which means at level form, it is non-stationary. But once you come to first difference, you see there are stars. So which means it is significant at level, at first difference, it is significant, which means you can reject the null. So at first difference, it is stationary, right? Which means it is I1. Understood? Yes, so you can do these kind of things. You can tabulate your results like this. And one last thing I will show you now before you go is that I have good news for you. The good news I have for you is, yes?
So this is stationary, right?
This one?
It's my stationary.
Okay, here you see the statistic, the test statistic is smaller than critical value, right?
So we can't.
So you cannot reject.
So it's stationary.
And what is the null hypothesis? Stationary, because it is KPSS, which means it is stationary.
Good.
So first of all, you need to know the hypothesis for the unit root test, ADF and PP, and the KPSS test, which is stationarity test. Once you know the hypothesis, then you can know if you're rejecting or you're not rejecting. It's easy. Okay, so the good news I have for you is that, remember, if you're doing this unit root test, for each variable, you have to take each variable and you test both level and first difference for each test using each of the models. It takes time. If you have like 5 variables, it's a whole difficult thing. So there is a way you can do all of them at once, but no, I cannot. I will not show at the first because you need to know this first. So come to add-ins. You see add-ins here, but you need to download it. Me, I have it here because I've downloaded it. You see here, I have all unit root tests. You in EViews, you will not have it because you need to install it. So if you come to add-ins, you see here, come to download add-ins. If you come to download add-ins, and if you scroll right down, you see, you see URL all? Unit root all, means all unit root. You see, I have it installed. So in your case, for instance, if you want to install something, if you click on it, then you can click here, install. So you need to install it. I'm not so sure. I don't know. So if you come here, you come right down, you see URL, that is all unit root. You install it. Once you install it, you see here, you will have, it will appear here, all unit root tests. So if I come here and I click all unit root tests, I just type the name of the variables. Lean CO2, is it capital letter? Lean CO2, lean FD, lean GDP, lean population. Just type the variables names, and then you see here, if you choose ADF, it means it will give you ADF tests for all these variables at once. If you choose PP, it will give you PP or KPSS, but you can choose ADF and PP. It will give you ADF and PP for all of them.
For the 3 levels, I mean.
For all the levels. So once you choose it, of course, you can choose a criteria you want to use. Do you want to use Schwarz criteria or Akaike? Just leave the default, leave Schwarz, and click OK. You have your results. So you see here, for instance, this is carbon dioxide. You see each of the models. You see this is 1 model, 2 model, 2. I think this model should be, let me see. This model should be the general model with trend and intercept. This one should be, it's even written down here. Okay, this one is with constant only. If you look at it, down here, with constant only, which means intercept only. This one is with trend and intercept, and this one is non-model, neither trend nor intercept. And you see they are giving you the results at level and also at phase difference. And this is PP. If you come down, you see ADF. So you have all the results at once. Maybe in the exam it's faster for you. You can just have your results at once. So you have ADF and PP for all the models. Then you can go back and do the one for KPSS. It's easy, right? And you can interpret it. When you see no here, this no means it is not significant. This no, all this no means not significant. These 3 stars and 1 star. So you see, if you, I think down here they have written something. 1 star means significant at 10%, 2 star means significant at 5%, 3 star means significant at 1%. No means not significant. So you know your hypothesis and you can interpret it.
And not significant means not stationary.
Yes, of course, you know this is PP and KPSS, sorry, PP and ADF, which is unit root test. So for unit root test, if it is non-significant, it means you cannot reject the null, which means it is non-stationary, it has unit root. But if it is significant, it means you reject the null and accept the alternative, which means it is stationary, it has no unit root, right? So I think it's easy for you to do all at once, but you need to know how to do it one after the other. Okay, so that is it for unit root. Next week, we'll do co-integration, vector error correction, and Granger causality. Then following week, we'll do AR root 0, right? Everything fine? Okay. Okay, yes. Sorry for taking your time. So I'll stop recording now. You have investment appraisal?
Yeah.
We have Hassan Hoja.